Within a habitat, there can be quite a bit of variation of solar radiation and wind speed. Solar radiation is much less in shade than it is in sun, for example. And also, wind speed varies with height above the ground and with the presence of objects that can act like windbreaks. All these factors will affect the operative temperature. In nature, animals and plants are acutely aware of this variation, and they'll exploit it to benefit themselves. If we're to understand how they do this, we must have some idea of what the range of operative temperatures is in a habitat. In short, we must have a way to characterize the thermal environment. We'll now show you one way to do this by using copper cylinders as operative temperature thermometers. These copper cylinders roughly mimic the shape of a large lizard. As you watch the video to follow, keep these two questions in mind. First, imagine you're a lizard living in a savanna habitat. If you wanted to keep your body temperature at some level appropriate for activity for as long as possible during the day, how would you go about doing so? And two, do you think there might be a trade-off between the benefits of exposing yourself to the sun to maintain a high body temperature and the risk of predation that might ensue from being exposed in this way?
We've learned a lot about how to measure operative temperature, what it means, and we've learned how it's influenced by air temperature, wind speed, and radiation heat exchanges. But it's a fair question to ask what that tells us about how animals and plants live in nature. One significant thing we can learn is the diversity of thermal climates that are available in an environment at any given time. We understand this intuitively. If, for example, the sun is out and it feels very hot, we can simply go under the shade of a tree and find relief from the heat. What we've done, obviously, is to seek out a microclimate where solar radiation is less intense, and hence the operative environmental temperature we are experiencing is cooler. However, different animals may experience the operative temperature in different ways than we do. The operative temperatures we experience will be dominated by radiation heat fluxes, whereas the operative temperatures experienced by small animals like a lizard may be influenced mostly by convection. We're going to do a little experiment now to illustrate the diversity of microclimates that exist in a habitat like this arid savanna, about 20 kilometers outside of Otjiwarongo. We prepared several animal proxy models, basically a short length of copper pipe that we've painted black. This is a good animal proxy model for an animal the size of a medium-sized lizard, for example. We're going to set these models out into the environment in various places to sample the operative temperatures they're experiencing. We're going to measure the temperature of these models using the iButtons that we've just calibrated. We're simply going to slide the iButton inside each pipe. We're going to seal the end with a wad of aluminum foil. We're going to hold it into place with black tape. And we're going to place these models around in the environment. Here's how we place our operative temperature models. Here's one right here. It's already prepared. We put a wire on it to hold it in place. We're going to just touch up that shiny end a little bit, just so it's nice and dark. We don't really care too much about the quality of the paint job. This is what it looks like. And the first one we'll put right out here in the full sun. And we'll just lay it out here like so. And we'll just put the wire in and lay it right on the ground like so. And that's going to experience full sun. Now we're going to place another one. We'll put the iButton in. We'll take a little piece of foil and put over the end. And seal it in place with black tape as we did before. We have a little piece of wire here that we're going to wrap around it and hold into place. We have to twist it with a pair of pliers because the wire is a little bit stiff. So we'll just do that quickly. All right, that's in place. We'll touch up the paint job again. Put a little bit of black on either side. And this one we're going to put into a place back here where it's likely to have full shade throughout the entire day.
Here's how we're going to place our operative temperature proxy models. In deciding where to place them, we're trying to get a pretty good sample of the diversity of microclimates in this habitat. That way, we'll be able to better judge where in a habitat an animal should be if it wants to attain a particular operative temperature. As you've already seen, we'll put one here on the open ground in the full sun. And you've already seen how we put one of the models into deep shade under a shrub. Just for good measure, we put one on this fallen tree in full sun, but exposed more to the wind. And we've tied one to this fence post, again in full sun and directly exposed to the influence of wind. We'll put one of our models here on an outer branch of this acacia tree. This one will be exposed at some times during the day to full sun and wind, but it may be shaded at other times of the day. We'll put one here in a cleft of the same tree. This one will be shaded pretty much the entire day, but it's located off the ground and exposed to the wind. We'll place another one here on the open ground under a tree where it's likely to encounter shade during at least part of the day. And we'll place another one here at the base of the same tree, but this one hidden within the grass and foliage. We'll let these run for a full day, allowing the iButtons to log their temperatures once a minute. After 24 hours, we'll come back to them, retrieve the model, and carefully note which iButton has been placed in each habitat. Okay, let's have a look at what the data say.
We've allowed our operative temperature models to record temperatures for more than a day. We've recovered them from the felt, and we've recovered the data from the iButtons. And now we're going to take a look at the results. Here are the data from one midnight to the next. In other words, temperatures for the entire day of the 11th of April 2015. Sunrise here was at 6:03 in the morning, and sunset was at 5:44 p.m. By the way, you don't need to note those times. You can look them up later using a table called an ephemeris. I happen to have used a tablet app called the Photographer's Ephemeris. All the operative temperatures we measured rose through the day, reaching a high in the mid to late afternoon and decreased overnight. No real surprises there, obviously. What is remarkable is the wide variation of temperatures in the different microhabitats within a larger habitat. The hottest temperatures are found on the ground in full sun. This makes sense. The ground receives direct sunlight, and because it's embedded deep in the boundary layer, it's exposed to only a slight wind and hence low convective heat loss. By our simple equation for operative temperature, this combination should produce the greatest temperature increment above air temperature. The lowest temperatures are found in shady conditions, in the shade of the grass at the base of the tree, and in deep shade below this bush. Again, this makes sense. Little radiation and the likely absence of convective cooling will keep the operative temperature increment small. In between, operative temperatures are affected to varying degrees by daily variation in solar radiation and convection. So, for example, operative temperatures on the fence post in full sun are cooler through the day than those on the ground. The model on the fence post is exposed to the same input of solar radiation as are the models on the ground, but up on the fence post it is exposed to more wind and hence higher convective heat loss. The result is a smaller increment above air temperatures and generally cooler operative temperatures. Similar results are evident for the model placed at the outer margin of the tree. The explanation is the same. High solar radiation, but also high convection results in a smaller temperature increment and generally cooler operative temperatures. The bottom line here is that there is much heterogeneity of operative temperatures in what we call microclimates. We'll have some comments momentarily about the biological consequences of microclimate heterogeneity. For the moment, let's quantify this heterogeneity. Here we've plotted the range of operative temperatures, that is the difference between the highest and lowest operative temperatures minute by minute throughout the day, and the standard deviation of these operative temperatures. Temperature ranges narrow through the night on the order of 1 to 2 degrees Celsius. During the daylight hours, though, the temperature range increases, reaching a span of nearly 30 degrees Celsius at some times. Microclimates also become more variable during the daylight hours. What's also interesting is the spikiness, if you will, of the range and standard deviation of operative temperature. During certain times of the day, the range drops abruptly, in one case here by about 20 degrees Celsius. Operative temperatures also become more uniform. What's happening here is the passage of clouds over the sun, a phenomenon of the late afternoon when cumulus clouds are forming in the sky. When that happens, of course, the quantity of solar radiation reaching the ground decreases, and with it the operative temperature. But what does this mean biologically? Microclimates provide organisms with the option of choosing their environmental temperature. The wider the range of microclimates, the wider will the choices be. Let's see how we can understand those choices. Suppose you're a lizard of roughly the same size as our operative temperature models. Lizards, being poikilothermic, will assume a body temperature very close to the operative temperature of whatever microhabitat they find themselves in. Let's make a further stipulation, that the lizard behaviorally regulates its body temperature. This is a common phenomenon in reptiles. Lizards will seek to keep their body temperature within a certain range. Let's say, for the sake of argument, that a lizard in a given environment will seek to keep its activity body temperature somewhere between 30 and 35 degrees Celsius. What are its options for doing so? To make the options easier to see, I've put together a table of operative temperatures throughout the day. The rows represent time of day, from one midnight to the next, and the columns represent the various microhabitats where we placed our operative temperature models. I've color-coded the table entries. If the cell is green, that represents an operative temperature that is between 25 and 30 degrees Celsius. If the cell is colored pink, this represents an operative temperature from 30 to 35 degrees Celsius. And if the cell is colored orange, the operative temperature is from 35 to 40 degrees Celsius. During the night, we see that the options for attaining a body temperature even close to the preferred range of 30 to 35 degrees Celsius are essentially nil. There is simply no microclimate available then that would allow the lizard to attain its sought-after body temperature. The lizard will simply have no choice but to hunker down and find a shelter, like a burrow or a nook among some rocks, or in a tree where it can inconspicuously wait out the night. During the daytime hours, when operative temperatures come to be driven by solar radiation, the lizard's options increase. Beginning at about 7 a.m., two of these microclimates, on the fence post in full sun and on the ground in full sun, can provide operative temperatures of from 25 to 30 degrees Celsius. It's not the best option, but as we say, it's a start. If the lizard wants to get an early start on its day, its only options are to emerge from its shelter and to bask in the sun, either right on the ground or in a convenient high spot, also in direct sun. Starting around 8 a.m., the options for suitable microclimates start to expand, with several microhabitats now having conditions that will allow the animal to reach operative temperatures ranging from 25 to 30 degrees Celsius. Now, though, there is only one microhabitat, sitting on the fence post in full sun, that will allow the lizard to get its body temperature up into its favored range of 30 to 35 degrees. Any lizard that chooses this site to begin raising its body temperature will get the jump, so to speak, on all the other lizards with which it's competing. By about 9 a.m., something interesting starts to happen. Microclimates that were favorable earlier, like sitting on the fence post in full sun, now become too hot, and the best site is now the stump in full sun. Through the midday hours, from 11 a.m. to 3 p.m. or so, the range of microhabitats that provide suitable microclimates expands considerably. Now, lizards can find suitable microclimates in a variety of situations: on the open ground, in the partial shade of a tree, on the branches of trees, and, once the wind picks up, back up on that fence post in full sun. Other microhabitats have become too hot, though. As the day winds down, the options for maintaining a suitable activity body temperature start to diminish. By 5 p.m., only 3 microhabitats, sitting in full sun on a branch of a tree, in a nook in a tree, and in the open ground at the base of a tree, provide suitable microclimates. 30 minutes later, there are no options left. So, what have we learned with this exercise? What we've learned mainly is a method for characterizing the thermal environment. If you're interested in understanding how organisms fit into the physical environment, it simply won't do to measure a single air temperature or even a single operative temperature. You must account for the diversity of microclimates in a habitat. We've just shown you how this can be done, and done in a biologically and biophysically realistic way.